Welcome to class. You hear me okay? All right, today we are going to wrap up chapter 2 briefly. We won't spend a lot of time on it. And then we're going to dive into thermodynamics, and it will be fantastic. So let me recap where we left off last time. Well, maybe before we do that. Today we will test out clickers. Nothing that you answer today will be worth points. It's all worth 0 points, but you can see whether or not your clicker is working at least, right? So to do clickers, if you have the physical device, then you put in the receiver channel as 41. And if you're using the ResponseWare app, then you type in this as the session ID. That session ID will change every time that we come to class. Every time I start up Cloud, it assigns, I think, a random number. So that won't be the one you use all semester. So always watch. This thing will sort of float on top of OneNote, and you'll see it there. And when we're ready, I'll just click start, and we'll see questions pop up. It won't be for 15 to 20 minutes. So that said, let's finish up chapter 2, which was talking about these energy potential wells. And at the very end of class last time, we'd finally gotten to something that was starting to look useful, right? We said, okay, the depth of this well should correlate to the melting point. And somebody said the deeper the well, the higher the melting point. And the way that we can think about that is as you're adding energy to this system, think about the atom that's at its equilibrium position, right? So it's at this lowest energy. If you start to give it energy by heating it up, you're basically letting it move around at the bottom of this well, right? As you give it more and more energy, you're letting it occupy more and more of these states, and it could eventually climb out of the potential energy well, right? Or in other words, it could move all the way up this curve and to the point where these two ions are infinitely apart, or we call that melting, right? They're no longer interacting with another. A liquid, the atoms are not interacting the same way as in a solid. They're free to move away from one another, right? So the deeper the well, the higher the melting point. Therefore, if I were to give you a plot of this material, let's actually redraw it. Oops. Switch this to stroke, right? If I were to give you a plot on an exam, and I would say, where's the metal, where's the polymer, and where's the ceramic, the plot might look just like we saw. You're going to have one that's deep, like that. You're going to have another one, which is a little bit shallower. And then maybe even one more, which is quite shallow. Right? So which one is which? Obviously, the one that's the deepest is the highest melting point. Is that your ceramic, your metal, or your polymer? Maybe turn to a neighbor and discuss. All right, I'm hearing only ceramic, so good. It is definitely your ceramic. Therefore, the red line is your metal, and the green line will be your polymer. Again, what is a polymer? We'll talk way more about it later this semester. That's plastics, right? The plastics, they melt at a much lower temperature than the other ones, okay? So we can clearly get melting point out of these, and that's nice, but we can get a lot of other useful information. Other things we can get out of them is things like stiffness or even coefficient of thermal expansion. Let's start with stiffness. So stiffness, it's a measure of what? If you've got two atoms, what is stiffness measuring? Anybody have a thought? Let me pick on, is it Morgan? What do you think?
How bendable, ductile something is?
Yeah, right? Or if you have two atoms and you pull them apart, a stiff material will be easy or hard to pull apart? Hard, right? So therefore, if we go back to our force diagram, we start thinking about force in terms of deformation, this should tell us something about stiffness. And in fact, it does. What we have to do is we have to take the derivative of the force expression, dF dr, right? We're going to take dF dr, and we're going to evaluate that derivative at a specific point. And that specific point is when r equals r naught. So that's right here. So in plain English, what does that look like? I said we're going to evaluate the derivative of a function at a certain point. What does that look like? No, close, good guess.
What is the slope of the line?
The slope of the tangent line. Remember this from calculus? If you had a function and somebody asks for the derivative at a certain point, they're asking you to identify the tangent line. What's the slope of that tangent line? So let's draw it. At that point, there's our tangent line. Yeah, Rob?
So you said that corresponds to what value?
Well, I'll show you in just a moment. This right here, this dashed line, since it's intersecting this green line only at one point, and that point is at r equals r naught, then that is df dr the derivative of the force expression evaluated at r equals r naught. And the slope, basically, of that is our Young's modulus. Yeah, question?
What is the units of R?
Unit is distance. Good question. You could do it in meters or angstroms or nanometers. It's a unit of distance, right? Normally when I plot them, if I do a question where it's plotted, I'll do it in angstroms. Because when you think about interatomic distances, they're on the order of 1 to 5 angstroms, right? Carbon bonded to carbon is like 2. Bigger bonds could be like 3, 4, or 5. So that's roughly the order of magnitude we're talking about. What is an angstrom? That's 1 angstrom is what? In meters. That's 1 times 10 to the negative 10 meters, right? So it's 1 order of magnitude smaller than a nanometer, and a nanometer is 1/1000th of a meter. So we're talking about tiny, tiny distances, right? That's your angstrom. All right, so if you have this, Young's modulus can be calculated from this. All we have to do is add one more thing. Young's modulus, which we write E sub y. Now, Young's modulus, that is what we call stiffness. We're going to come back to that way later on. You mechanical engineers who've had your intro course, you've already learned about that. But E sub y, that's not an energy. That is Young's modulus, and it is proportional. That's what that little funny squiggle sign means, that it's proportional. Not exactly equal, but proportional to 1 over our interatomic spacing at equilibrium, 1 over r naught, multiplied by this derivative of the force function, right? So meaning if I gave you information to have one of these potential inter-ionic force diagrams, and you had an expression for this curve, you could then calculate the stiffness of that material, which becomes really valuable, right? We'll talk about how you show that equation in just a moment. Okay, we talked about that. There's our stiffness. Let me briefly say coefficient of thermal expansion before I give you an equation for these. Coefficient of thermal expansion also can be achieved from these diagrams. How does it work? So again, at 0 Kelvin, if you had these things all the way down at the lowest temperature they could go, they're going to go to the lowest energy available. And as you start to heat them up, they're going to start to rattle around in that bottom of that potential well and start to occupy higher and higher average states, right? So at any given point, what's the average position between this point and that point? It would be maybe right there. Between this point and that point, maybe there. So you can see that our average position is actually increasing, right? The average interatomic spacing is increasing as you heat this thing up. That makes sense? Are there any questions about this? This only happens if you have a potential well which is asymmetric. And they are asymmetric, right? You almost always, for almost every single material, it is really steep on this side, and it's less steep on this side, right? Because they had different r dependence. One was 1 over r squared, one was 1 over r like to the 8th or 9th. Therefore, it's asymmetric, and as you heat it up, it tends to go towards larger values. There are some materials that don't expand at all. Quartz, for example, right? The crystal, if you have crystal glasses at home, that's quartz. Pure quartz doesn't expand at all. It's almost 0, which is really valuable for some things and it causes problems in other ways. Other materials actually shrink a little bit upon heating, which is really unusual. I think we'll talk briefly about that at some point later this semester. Any questions? Yeah?
Sorry, what were the axes labeled with those graphs?
On these ones here?
Yeah.
These ones, when you see it doing a potential well, then it's a potential energy well. So this is energy against interatomic spacing. Energy versus interatomic spacing. Good question. Right? So in one material, a ceramic, like we showed on the left here, with a deep potential well, this tends to be more symmetric. The deeper it is, the bottom part tends to be more symmetric, right? As opposed to, say, a polymer, it tends to be much less symmetric. So which one would you expect to have a greater thermal expansion coefficient? The polymer, because, like, again, you start out here, and by the time you start adding temperature, your average position with just a little bit of temperature is really taken off that way, right? Fair enough? So these diagrams are useful. Again, if you have a material that's compliant, let me draw it down here. If you have a compliant material, that's a material that's not stiff, it's compliant, and you were to draw its force versus interatomic spacing, say like a polymer, it would have a little rise like that. And the slope at the r equals r naught value is going to be much less. It's a much lower slope. So for a given unit of force, if you put in 1 unit of force, you can achieve much more deformation, much bigger separation in terms of r, right? So can I answer any questions on coefficient of thermal expansion or Young's modulus, which is your stiffness? Can I explain any of this again to make it easier to understand? Yeah.
So the higher the Young's modulus, the stiffer it is.
Yeah, the higher that slope, or meaning the higher the value of your derivative at that point, the stiffer your material. And that should make sense, right? Because you have to apply more force. If it's a high slope, you have to apply a big force to achieve the same separation in terms of R. So it's a more stiff material. Now, how do you relate, again, this was a ceramic and a polymer. Which one do you think would be stiffer, a ceramic or a polymer? Ceramic is definitely stiffer, right? And this point at the bottom of this potential well, that corresponds to R0, right? So if you remember something about energy, right? We said that you had your energy function, right? And we said that F equals dE dr. And then Young's modulus was basically you take that derivative again. You're doing like d squared E dr squared. You're evaluating that at r equals r naught, and you're multiplying it by 1 over r naught. But you're basically taking the derivative twice. Anybody remember from calculus when you take the derivative of twice, what did that look like on your original function? Yeah, an inflection point or curvature, right? So if this is our original, let me lower it so I can reach it. Right? If this was our original energy function right here, at this point, what's the curvature? Is it greater or less than this material right here? It has a greater curvature, right? If the curvature is greater, then the second derivative is larger, right? And we just said that your Young's modulus corresponds to the value of that second derivative. So it's not surprising to find that ceramics, which have a higher melting point and a stronger binding energy, are also stiffer by virtue of the fact that their second derivative is larger, right? Any questions on this? Yeah, in the red shirt.
You said that we were going at r naught, which is where the curve crosses the r-axis.
Where the force curve crosses the r-axis, right? Because that's where you have no net force, right? It's zero. The force on that compound is zero. If it had a force on it, they'd be moving. But since they have no force, they're staying put.
Why is that r naught? Isn't r naught at the far left on the vertical axis where r is 0?
So again, when you plot force, you identify the equilibrium position when the force is 0. Force net equals 0, right? There's no net force on your particle, so it's not moving. But that corresponds, in terms of energy, to the lowest energy, right? Let's draw a little line here to make it maybe clearer. Change colors. This is becoming like a scribble. This is the same point, right? The lowest energy is when it's going to be happy and it's stable in terms of energy. In terms of force, that's when it has no net forces acting on it. That make sense? Can I clarify anything else here? Yeah, Anthony.
So that first part of the curve on the red curve,
Okay.
say it's a black
Yep.
or whatever,
Okay.
that's basically it flexing, right?
When you say the first part, this part right here,
Yeah.
that's the repulsive. Basically, if you go from your equilibrium position to the left, that's you squeezing a polymer together, and it has some compressibility, right? It starts to resist you compressing it together, and it really takes off rapidly. It starts to cost a lot of energy to compress that polymer together. In this case, it's easier to pull that one apart for sure. Okay?
And then, well, so what would the material look like if it was like this? You know, some materials do break and it's compressed, of course. So, like, what would a material that broke more easily under compressive forces look like?
Let me pause that, and when we get to chapter 9, we'll first introduce fracture, because fracture is really what we're observing. And then chapter 7, we'll talk more about mechanical properties. So I'm going to pause that for now, and we'll come back to it.
Sorry.
But we will come back to that. No, good question. Yeah, question?
Is that force graph that you drew there, is that, no, down there?
Okay, this is force. These ones are energy.
Yeah.
Or this force right here.
That force.
Okay.
So is that an example of a stiff material or a soft?
Well, relative to the one that we drew above, this one had a higher slope. This one here. So this one would correspond to the deep potential well, like for the ceramic, whereas this one with a smaller slope would correspond to the polymer, because it has less of a slope. Okay? Okay. Now, way later on in this semester, we're going to learn about composites as its own chapter. We'll talk about, when you mix these different things together, how do you model them? But for now, because I don't want to wait to the end of the semester to talk about composites, let me just introduce one very simple rule, which is called the rule of mixtures. The rule of mixtures says the following. The property of your composite is equal to the property of your first component multiplied by the volume fraction of your first component plus the property of your second component times the volume fraction of your second component. You'll use this on your first homework when you calculate the density of nitinol mixed with aluminum, right? That you have 20% of aluminum, 80% nitinol or something like that. So if you take the density as the property in either of those and you have the volume fraction, you'll find that it meets in the middle. That's basically what the rule of mixtures does. It's saying that you're meeting in the middle. It's not always, it doesn't work for every property. There's some that it gets spectacularly wrong. You have to use a completely different model. But for a lot of things, this is an okay way to model it. Okay, yep. You could use it for stiffness, right? Now stiffness depends on how the composite's put together. Like it can break this rule, but it can be used for electrical conductivity, for strength. You can use it for a lot of things. But like I said, later on in chapter 15, we'll talk about how to modify it for actual composites. But for density, it works great. Okay, there's a lot of different bonds out there, ionic versus covalent. I'm going to skip this because I know that you've seen it in Gen Chem, and I'm going to trust that you can review it if it's not familiar in chapter 2. For the sake of time, we're going to skip this. But I do want to write out at least what the equation is for how to calculate what fraction of your bond comes from ionic versus covalent, right? And the equation is as follows. That's a terrible bracket. Right? It's going to be 1 minus the exponential of the quantity, negative 1/4, multiplied by the quantity of the electronegativity of your two atoms that you're interested in, subtracted from one another and squared. That's called the deviation. Right? So what do I mean by this? In this expression, the only thing that we don't know is chi A and chi B. That's the Greek letter X. They call it chi. So for your two different atoms, whatever they are, you know, nickel and chlorine or whatever it is, you look up the electronegativity for those two atoms. When you plug those into this formula, it will spit out a percent ionic character. So what things do we expect to have a high ionic character?
Things that are non-metal with metals.
Yeah, or another way to think of it, if we remember when we talked about electronegativity, things that really want that electron, like fluorine up here, really wants an electron. And things like sodium over there would love to get rid of its electron. So when you put those two things together, they have a very big difference in electronegativity. So if you plug them into that formula, it's going to come out to be almost entirely ionic, right? A very high percentage ionic. But other things, like carbon bonded to carbon, it has the exact same electronegativity. So if you plug that into this formula, what's going to happen? You get same number times minus the same number. That becomes 0. What's exponential of 0? 1. So then you have 1 minus 1. So you have 0% ionic, right? Completely covalent, right? So that's how you use this formula. It's kind of useful for determining, and I think that for me, one of the takeaways from this formula is we don't have to think of things as quite as binary as you learned in Gen Chem. It's not just ionic or just covalent. There's fraction, right? It's kind of ionic and kind of covalent. We can determine that fraction. Yeah, Griffin?
And then X stands for electronegativity.
That's the electronegativity of the two atoms you're interested in. In the back, is it bars in? Yeah.
So I was going to ask, and what if you put two metals instead of like carbon and carbon, so like two of the same metal? Then you still get 0, but it's not a covalent bond.
It doesn't, yeah, all this tells us is this tells us the percent ionic. If it's 0, it doesn't mean that it's covalent because it might also be metallic. So if it's aluminum and aluminum, I mean, that's a metallic bond. Fair enough? Okay, I'm going to skip the rest of these for now. If you have questions about bonding in general, these different types, please take advantage of our wonderful TAs. By the way, more of them are here today. Can I have you guys raise your hands? Here's 3 more of our TAs, unless I'm missing anybody else here. Great resources. They're happy to explain more of this stuff to you guys. Okay, let's switch now to talk about thermodynamics. Okay, our learning objectives for today are, we're going to identify what enthalpy and entropy are, and what is their role in thermodynamic reactions. We're going to be able to predict entropy, at least if something got bigger or smaller, right? We won't predict values, but we'll say bigger or smaller as a function of reactions. We will use tabulated values for these things to calculate the change in entropy or the change in enthalpy for a reaction, which becomes important. And then if we have time, we'll get to using Gibbs free energy as a way to bring entropy and enthalpy together, right? Because you need to consider both of them. And I don't think we'll get further than that today. Okay, so the one thing that we really, I'd like to teach in this class, but is not covered in this book, is thermodynamics, right? So chapter 16, it talks about electrochemistry, and electrochemistry is very analogous to thermodynamics, but it's not the same thing. So you're not going to find this in the book. So here you have to rely on our notes that I'm providing here in the course notes, as well as some nice tutorials. This one, Wisconsin, in their chemistry department, they put together a great, they call it a net tutorial, right? It's a tutorial on the net. It's great. It'll actually have questions where you can see if you got it right and wrong. I encourage you to take a look at it. It's short. It covers the same things we're covering today. So if anything was unclear today, I encourage you to treat this website as your reading for the thermodynamics section, right? Now, why do we care about chemical reactions as material scientists or as engineers, right? If you're getting a mechanical engineering, why do you care about reactions? You don't picture yourself as mixing things up in a beaker in your job. Why should you care about it? Let me pick on, is it Jonathan? The black cat? I'm guessing not. What's your name? Yeah. Randall. Why should you care about chemical reactions?
I have no idea. That's why I'm here.
That's why he's here. Fantastic. Is it Ali? What do you think? Why should you care about it?
So it predicts. So it can predict anything that happened in the.
Whatever's going to happen to it. What might happen to it? I heard somebody say corrosion, I think. Maybe? Or maybe this is what I want to hear. Corrosion. Corrosion will definitely happen, and we can predict whether or not it will happen, right? We can even predict rates or how likely it is, if it's more or less likely. What else? Rust is a type of corrosion, absolutely. Oxidation versus other types of corrosions. Yeah, in the back, Anthony.
So if you want to know if it's going to react with any other materials, you're going to...
Yeah, absolutely. What if can you bring two metals together? Will it be okay if they're bolted together? Is that a non-issue, or is that okay? Can you put salt, like, anybody own a house yet? Anybody own a house yet? I learned that you're not supposed to put salt down to get rid of ice, because it will do what? Yeah, you'll ruin your concrete over time. It starts to look, you ever seen concrete that's like chipped and like destroyed? A lot of that is due to salt, because we salt it, right? So we'll learn about some of those things, and that's why we should care about reactions, right? Because as engineering materials, as we use them in their different use environments, they're going to be facing reactions whether or not you like it or not. They're just going to be happening. So how do we write our reactions? Again, going back to Gen Chem, you have your reactants, and you have them turning into products. You can start out with lots of different reactants turning into just one product, or you can go the other way. You can have just one reactant that gets broken up into lots of different products. But I think the key thing is to don't think of it as a linear process where it's always just reactants to products. Think of it in terms of this double-sided arrow, meaning it's going to go both ways. It's actually an equilibrium. At equilibrium, when your reaction's at equilibrium, you have just as much turning into products as you have products turning back into reactants, right? We'll give some examples of that later. And critically, the type of reactions that we care about oftentimes are redox reactions, which are reduction-oxidation reactions, meaning that they involve the exchange of an electron. Right? You've got electron transfer, something that's giving up its electron, something else that's picking that up, right? The easy way to remember this, oxidation reduction, is the oil rig, right? Mnemonic device. Oil rig. Oxidation is loss. Reduction is gain. So if you can identify a chemical species that loses an electron, then it is oxidized. If you identify one that's picking up the electron, it's being reduced. And if you have a reaction that has an exchange of electrons, you have to have both of these things, right? So if you have a redox reaction, you are always able to write out the half-cell reactions for both types. Let's give you an example. Let's talk about electrolysis. Anybody heard of electrolysis before? What's electrolysis, Griffin?
It's basically where you split water.
It's splitting water. You start out with water, which is what? H2O. You're going to split that into hydrogen and oxygen. This is great for a lot of things. We use oxygen all over the place. Hydrogen we're using more and more all over the place, right? It could be a fuel that we use. Well, oh wait, save a few chapters. We'll talk more about electrolysis. It's a big deal. So how do you split it? Any ideas? How do you split water into hydrogen and oxygen? Yeah, you run a current through it, basically. You pass a huge current through it, and that breaks that chemical bond and temporarily liberates your hydrogen and your oxygen. And if you have a way to then separate those, then you can perform electrolysis commercially and actually start selling your hydrogen and oxygen. But you have to have some way to deliver electrons from one side to the other. So here's what the reaction looks like. You've got H2O as a liquid. So a little subscript L is going to be for liquids. We're going to turn that into one molecule of H2 gas. So a little G to indicate a gas. And you're going to generate half of a molecule of O2 as a gas, right? So this is the full equation. Now, does anybody see where there's the exchange of electrons involved in here? Is it obvious? Maybe, how about this? Turn to a neighbor and identify which species has picked up an electron, which one has lost an electron. Okay, we're going to identify the oxidation and the reduction reactions, and I'm going to pick on, let me ask Cody, and I think it's Daisy next to him, I think, to do one of each. Which one looks like it's gaining an electron? You have an idea?
Well, it's just following our full equation doesn't necessarily explicitly show.
Yeah, the full equation, it's not obvious at first glance where the electrons are coming or going. Anybody want to help them out? Anybody see where maybe there's an involved of an exchange of electrons? Yeah, is it Arthur?
Yeah. The oxygen atom pairs with the two hydrogen atoms because it wants two electrons. So when it goes away from it, it loses two electrons, and then the H2 gains two electrons.
Yeah, what you're saying is that this guy started out as a 2 minus, and hydrogen started out as a +1, is what you're saying, right? And yet over here, what's happening? Hydrogen, does this have a charge? Does this have a charge? Those are both elemental, right? So basically we must have had the following. We must have had, I'm simplifying this, but we must have had hydrogen ions pick up one electron to form 1/2 of an H2 gas molecule. Meanwhile, you must have had, we'll just write it out like this, we'll say 2 H2Os, created oxygen gas by separating out these 4 H plus ions and 4 electrons, right? So basically this oxygen was 2 minus before. By the time it turns into oxygen gas, it had to give up 4 electrons, right? So this exact reaction is not important, but this same type of reaction where there's this exchange of electrons is very important, and it's involved in understanding corrosion, especially electrochemical corrosion, which is a big deal. So we'll come back to it. Okay, again, if you've taken chemistry, you would have seen how to balance equations. We're not going to go over it for the sake of time here. If you feel like you couldn't balance any of these equations, or if you want to just test it and try it out, I encourage you to try it and then work with the TAs and make sure that you know how to balance these equations. The main thing is that the same number of electrons need to be on both sides of the equation, right? And the same number of atoms of different types have to be on both sides of the equation. We're not going to delete material, right? I guess in like nuclear reactors and stuff you change elements into different types of elements. We're not doing that in this class. Our chemical reactions are only involving the exchange of electrons. So now here's the key question I want to get to, and the whole reason we talk about thermodynamics is, how do you know if a reaction will go forward or not? So turn to a neighbor. How on earth do we know if a reaction goes forward or not? Okay, how on earth do we know? Let me pick on in the pink shirt. I think it's Brad. I think that's you? It may not be. I think it is. How do we know? You're right. If something happens, then we say it's spontaneous. Now, how do we know whether something's spontaneous or not? Spontaneous is an important word. We'll come back to it. Anthony. That's also cool. All right.
Basically, don't you have to analyze the free energy of the system and the...
Yeah. Now, you used a special word there. You said free energy. Let's just talk about energy for a minute. What do we decide is the reason that everything in the universe happens? It happens for a reason. That reason is, Rob?
Because it's lower energy.
Because it lowers the energy. It started here, you did something, and it lowered its energy. So it's happy. So it's spontaneous. It happens, right? So what we need to know is for any given reaction, say gasoline, in your gasoline, you put it in your engine, you hit it with that marvelous spark plug inside that piston, and whammo kablamo, magic science happens, right? And out comes gases. We know that this will happen repeatedly. You can test it, it'll happen, right? We're missing oxygen. I missed oxygen. You know oxygen too. Right? That will happen reliably because that always lowers the energy of the system. And if you start out with CO2 and H2O, something that we could, we breathe out CO2 and H2O all the time, that doesn't just automatically turn into gasoline vapor, right? We're grateful for that, right? I don't know, are we, right? Because it's not energetically favorable. That would go up in energy, right? So thermodynamics as a discipline is the study of heat and energy in its relationship to, heat in its relationship to energy and work, right? So it's all about understanding how heat goes into things, hence thermodynamics, right? So in order to understand energy and how energy changes, we have to introduce some key variables. First off, temperature, right? Then pressure, then mass, volume, and U. U is going to be our internal energy. And remember, and this is critical, that we can't delete or create energy. We can simply convert it from one form to another. If I have this sheet of paper and I raise it above the table, it has a potential energy relative to the base of the table. And when I drop it, it converts that potential energy to kinetic energy, right? You can also convert to in and out of chemical energy, right? Energy is stored in a bond. You can temporarily release that energy when you break the bond, like we do in the gasoline in our engine, right? So you have to just convert from one form to another. And that's really what the first law of thermodynamics is all about. The first law of thermodynamics is really simply restating this, that it's neither created or destroyed. Here's how we write it. We say that the internal energy, U, equals, we've already defined U. We're talking about du, the change in our internal energy, right? If it's going to go up or down, then that has to go somewhere. Du must be equal to dq minus P dV. So this is heat. P is our pressure, and dV is our change in volume. So what this is saying, if something changes its internal energy, that has to manifest itself as either absorbing or releasing heat, or doing work on the system around it, right? If it's at a certain pressure, imagine like a balloon. When I blow into a balloon, it stays roughly at the same pressure, but it is going to expand, right? So it's doing work on its surroundings around it. And this is just saying that we're not deleting energy. It has to be converted to one form or another, right? Now, next up, let's talk about enthalpy. Enthalpy is a measure of the total energy of a given, thermodynamic system. So H, our enthalpy, it should include internal energy for sure, right? The total energy must include the internal energy, but it's also going to include energy involved with doing work on the system around it, P times V, right? So what will the change in enthalpy be? Well, as the enthalpy goes up or down, now we're talking about the derivative, dH. So dH is going to be du. And then how do we deal with derivatives of two-state functions? What do we do? The product rule, right? Is that the same thing as the chain rule? Is that different? I don't remember. That's definitely different. I'm getting a lot of shaking heads, right? It's P dV plus V dP, right? So from calculus, somewhere you saw this. Any questions so far on this? We talked about our total internal energy. We talked about our total enthalpy. Now we're talking about the change in enthalpy. And take a look at this. du plus pdv right there. What is that? Hint, it uses this equation. du plus pdv. If you bring this pdv over there, that's just dq, right? dq. Right? That right there is just dq. And then we have this vdp. So that's the volume of your component times the change in pressure. The reason that we care about enthalpy is because under most circumstances, is pressure changing? Fine, there's certainly examples where it is. But most of the time a chemical reaction, if I set a piece of metal here and let it rust, that's all happening at constant atmospheric pressure, right? So dP, if that's constant, then dP goes to 0, and that whole term goes away. This is convenient because then we can start saying, okay, the change in enthalpy, the total energy of a system, if it's done at constant pressure, which a lot of things are, is only the heat that's generated or lost, right? So enthalpy is whether something, maybe you've heard this in chemistry, is exothermic or endothermic, whether it absorbs heat or gives heat off. That's really a measure of the enthalpy. Now, this doesn't work if you have something like a reaction chamber where the pressure inside that chamber can change as the reaction goes, right? Then you have to use a different, you have to consider this term. That's what you have to do. You have to consider that term. It doesn't just go to 0. But for a lot of things that we care about, enthalpy change is just the heat evolved or absorbed in a chemical reaction, okay? And again, we say it's exothermic if that heat gets released, meaning it feels warm. and it's endothermic if the heat gets absorbed. Okay? Now, I'll come back to whether they're additive or reversible in a moment. Come back to that in a moment, actually. Let's jump now to entropy. So enthalpy is the first critical thing that we have to talk about in material science. And I'll say that enthalpy normally has to do with bonds. Bonds being broken, changing, satisfied or not satisfied. That's enthalpy. The next thing we have to care about is entropy. What on earth is entropy? Yeah. Yeah, the degree of randomness. That's the usual answer you get here. Here we've got it from the book saying, or not from the book, from a different book, saying the number of specific ways in which a system can be arranged. So imagine for a moment you had a paint bucket and you filled it full of red marbles, halfway full, right? And then you take and you fill the top half of that bucket with white marbles, right? So we would say the entropy of that system is some value, right? There's some way that these marbles, they can move a little bit, but the white and red are separated. If you were to shake that thing, what will happen to the red and white marbles? You put the lid on the thing, you shake it, what will happen? They're going to start to mix, right? Can you ever imagine a scenario where reliably you start out with a mixture of red and white and you shake it and it separates? If they're the same type of marble, of course.
Well, it depends on how you shake it too. Like if you just jiggle it, the heavier stuff will sink to the bottom.
Yeah, if there's different densities, you betcha, then this is panning for gold and you can separate them out that way, right? These are the same marbles, just different colors. And the point is, it's never going to separate into a red layer and a white layer. It's always going to move to a disordered state, right? We see randomness like an example of that all around us all the time. So what I'm getting at is the second law of thermodynamics. The second law of thermodynamics is that entropy in a system, at best, stays constant and almost always increases, right? Maybe you've heard in high school chemistry class or something, they talk about the universe is always expanding. Because as it expands, it's increasing the entropy of the universe. The universe won't collapse and we will all just, collapse and disappear, right? If anything, it's going to expand, right? Things are becoming more and more disordered, right? These are things that are just unviolable principles of thermodynamics that we just agree with, right? Now, what would be useful is actually relating this to materials. Why do we care about this degree of disorder? It actually explains some interesting phenomena. So, I have a demo. So I need 3 brave volunteers. No one's going to volunteer to enter this class. 3 brave volunteers. Anybody? Okay, Elise is brave. She'll come do it. Anybody else? Go. Do it. Come on down. Griffin. We can do 4. Come on down. Okay, come grab a rubber band. What I'm going to have them do is these guys are going to be your thermometers for you. What they're going to do is take a rubber band and we're going to perform an experiment. You might have seen this in a high school chemistry class. They're going to take the rubber band and first thing I want you to do is stretch it and then put it on your lip or your chin or something, somewhere you can feel temperature well. I don't know why. That's better at sensing temperature. According to YouTube, is what people do, right? Stretch it and tell me if it gets warmer or colder. Go ahead. Stretch it, warmer or colder. Let's just sense the temperature. Right? So he thinks warmer. 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 4 witnesses. All right, now. So actually, I think we have some clicker questions about this. That is tiny. I can fix this. Wow. What has happened?
Pinch to zoom.
Pinch to zoom? Hey, fantastic. Pinch to zoom. Okay. So, all right. So they just stretched it and it got warmer. Now the question is the rubber band contraction reaction exothermic or endothermic? So what I want you to do is now take it and stretch it and hold it there for a minute so all that warming that happened gets equilibrated with the environment. So hold it there, stretched. Now what I want you to do is carefully release it quickly and tell me what you feel. Well, you got to put it on your face.
I can feel it in my fingers though.
Cooler?
Yeah,
Cooler? All right, go ahead and you can sit back down. Okay, so the question I want you to answer on your first example of a clicker question is the rubber band contraction reaction exothermic or endothermic? So go ahead, get your answers in. We got 70, so a few more people got to answer. Go ahead. So he's asking, when will the clickers be worth points? Starting this coming Wednesday, you will have clickers worth points. So today is just a test that yours is working, but they'll be worth points starting Wednesday. Okay, so what do people think? I'm going to go ahead and end this for the sake of time. People think endothermic or exothermic. The contraction process, people think mostly endothermic, and it's right. It's spontaneous, and yet it's endothermic. Is that puzzling to anybody? Think about it. something is endothermic, it absorbed energy because it got cool, right? It was absorbing energy, but it happened spontaneously. Is that puzzling to anybody else? Something should, remember from chemistry, maybe you saw like a favorable spontaneous reaction is one that's exothermic. That should sound familiar, right? It produces energy. This is basically saying, like, why aren't like materials like rubber bands just gobbling up all the energy in the universe to contract, right? This should be concerning, right? Let's ask another question. Gosh, it's driving me crazy. All right, is it spontaneous, true or false? I'm just going to skip this. Again, these aren't worth points today, so don't worry about it. It's clearly spontaneous. You stretch the rubber band, it will snap back shut automatically, right? Next one. All right, how about this? For an endothermic reaction, so one that absorbs energy, is that forming or breaking bonds? This one's harder. Endothermic, absorbing energy, does that form or break bonds? Okay, get your answers in. Are we forming or breaking bonds? Okay, I'm going to end it. Get your answers in. Yeah, this one's always split. People have a hard time with this one. Endothermic reactions, does that form or break bonds? Here's the right way to think about it, I think. This helps me remember it. You start out with a molecule of gasoline, right? With your molecule of gasoline, right? Some chain of carbons, right? It doesn't look quite like that, but it's kind of like that, right? That's a bunch of carbon bonded to carbon and hydrogen and other stuff, right? When you convert that in an engine to exhaust, what's the exhaust made of? CO2, H2O. So did you break bonds or make bonds in that process? You did both! That's what's key here. People think of gasoline and they know that burning it is exothermic. It gives off a ton of heat. And they think, oh, if I burn it and that's breaking bonds, then exothermic should be breaking bonds. But you're missing the fact that when you break it, you break that carbon bonded to another carbon, but then you make that carbon bond with oxygen. Overall, you make more bonds than you created. All those individual things that were bonded to each other in the gasoline molecules, they form all these things. So actually, breaking bonds is an endothermic process. And that should make sense. Think like, if we have Ryan here and Nicole next to him, if that's like sodium and chlorine, sodium chloride is bonded to each other. If it was exothermic for them to break that bond, that wouldn't make sense in terms of our energy potential well. We know that to separate these two ions, they have to go up in terms of energy. You'd have to pour energy into it. So breaking that bond must be an endothermic process, right? And therefore forming bonds, when they reform again, that must be an exothermic process. Griffin.
So when gasoline is burning, it's actually, what keeps it burning is the CO2 and all the things together, it throws more heat.
Exactly. When the CO2 forms, when that oxygen bonds with those now newly liberated hydrogen and carbon atoms, that produces more heat, and so it continues, right? It overall is an exothermic reaction. There's an endothermic part to break the gasoline molecule, then it becomes exothermic. All right, let's go next one. Okay. As you stretch this rubber band, right, it goes from being unstretched, and now I'm stretching it. Think of it the other way. We start out like this. We know it's endothermic to release it, right? We agree? And we also know that going from this to that, since it's endothermic, that we broke bonds. So the question is, what on earth bonds are we talking about? What do you think? A, B, C, or D? What bonds did we break? Okay, A, B, C, or D, I'm going to end it. What bonds are breaking? By the way, if you have questions, raise your hand. The TAs are happy to wander around and do their best to explain it. They haven't seen these ones ahead of time, but they're still pretty bright. They can help out. Okay. The bonds that break, we're going to go ahead and see the answers. I'm curious what people think here. Okay, definitely most people think van der Waals bonds. From chemistry, you remember, a van der Waals bond is one, you start out with rubber, and we'll talk about this later this semester, what polymers are made of. They're chains of long strands that are, imagine a bowl of spaghetti. If you looked inside a bowl of spaghetti, that's kind of what polymers look like. It's long chains, but they're all tangled up. And when you stretch a rubber band, what you're doing is you're taking a glob of spaghetti and you're stretching it. Now, what does it look like? It looks like a bunch of chains that are kind of lined up with one another. When they line up with one another, you create van der Waals bonds between them, right? So you created bonds by stretching it. When you release it, it's breaking those bonds. Question is why, right? We just got done doing a whole chapter on bonding. We said that there's a potential energy well. So when you created these bonds, you created the potential energy well. It's now sitting at the bottom of that well. Why is it ever spontaneously breaking those bonds? What do you think? So let's do the next question. How about this? If a rubber band is stretched by attaching a hanging weight to it, and then we heat that rubber band with a blow dryer, what will happen? Will it expand, contract, or nothing? Rubber band is stretched with a weight on the bottom. I then heat the whole rubber band with a blow dryer. Does the rubber band expand, contract, or nothing? Okay, get your answers in. Will it expand, contract, or nothing? Okay, let's see what people think. Okay, most people think it will expand. After all, we did just learn about thermal expansion. We said when you heat things up, they climb out of that potential energy well. This is intentionally misleading. And by the way, on a question like this in class, I would never make this worth points because I know that most people will get it wrong. So I'll have it as a clicker point, but I'll give you a point for right or wrong answers. I'm not trying to trick anybody in lectures. I know you come to learn. Stuff that you should have known from reading, I'll make those worth, 1 or nothing points. But stuff like this, I would make both worth it. Now the question is it going to expand or not? Let's take a look at the video. So thanks you to the internet, I don't have to do this for you. We can just watch it. So he's got a rubber band hanging there by a weight. He's going to hit it with a blow dryer and watch the height of this thing relative to that ruler. Check it out. This is blowing your minds? My mind is totally blown, right? And then they let it go and it drops back down by the end, right? When the hair blow dryer removes. So now somebody try and explain this to me. Does this make any sense? Anybody have a shot? So Hayden, what do you think's going on here?
So the process of stretching the rubber band is exothermic.
Exothermic.
Yeah, so when
Yep.
you apply heat to an exothermic reaction, it goes the opposite.
It goes the opposite. That's a perfect way to think of it. Anybody not clear on that? Want to hear it one more time? Let me ask Anthony. Explain it one more time.
Oh, I was wanting to hear it one more time.
Oh, anybody else want to try and explain it in their own words? Griffin, go ahead.
It's already gaining energy, but it doesn't want any more energy than it already has. So when you throw energy into it, it wants to get rid of it back out, right?
Yeah. So there's something called Le Chatelier's principle. Anybody remember this in chemistry? How does Le Chatelier work?
Well, since heat's a product of this reaction, if you add heat, your Le Chatelier's principle says it's going to shift towards the reactant side.
Yep. The Chatelier principle says reactants and products. This can be heat or it can be actual molecules, right? Let's say that you're converting gasoline to CO2 and H2O. What will happen if you consume all of your gasoline, right? Now you just have a vessel full of CO2 and H2O. Can you then go further forward in that reaction? You can't. It's actually not. In fact, you'll have some, it might be minuscule, it might be tiny, but you'll have some actually going backwards. Now, in the case of gasoline, it's not going to be very much. Other stuff, it can meet right in the middle, right? You can have an equilibrium where it reaches in the middle. So what Griffin was saying, I think it was Griffin, one of you guys was saying, in this case, we know that when you stretch it, heat is a product. And if you add more and more heat, it's going to actually spin it the other way, right? Because you have too much product, so it's going to start sending it back towards the reactant state, okay? Why do I like to talk about this? Because it's a great way to describe why entropy can't be ignored. In this case, with the rubber band that's unstretched, that's your bowl of spaghetti, right? Totally tangled. We could say that is a very disordered system. When I stretch this rubber band, that's again, it's taking my spaghetti noodles and it's aligning them up. So I increased the degree of order in that system. I made it less disordered, and the universe doesn't like that, right? That costs energy. That has to be made up somewhere, right? So what we need is a unifying term that brings together both enthalpy and entropy. We can't consider one of them separately because they both play a role. In the case of a rubber band automatically snapping shut, that's an example of a reaction that, even though there is an enthalpic component to it, it's dominated by entropy. So in the beginning of class next time on Monday, we'll introduce a new variable, which is one that's useful because it combines both enthalpy and entropy together. We'll start there next time.